So I want to talk about related rates. When we did implicit differentiation, we took the derivative with respect to x. So whenever we had to mess with the y, we always tacked on a dy dx. But there's no reason we have to take the derivative with respect to either variable. If we want, we could take the derivative with respect to w. So if I had, say, x squared plus y squared equals x, I could take the derivative with respect to w, and I would say, okay, 2x times dx dw, because I don't know how that changes. 2y times dy dw equals dx dw. So I've got all these different rates here based on a different variable. That's what we do with related rates. So we actually take the derivative with respect to time. With respect to time. If two things are related by an equation, then the rates that they change would also be related. So let me do an example, of course. So let's say you're standing on a ladder. Let's draw. There's a building. There's a ladder. We're going to call this a 13-foot ladder. So let's say you are standing on a 13-foot ladder, and your puppy dog, who doesn't like you, starts pulling it this way at a rate of, let's say 1 foot per second. My question is, how fast are you falling once the bottom of the ladder is 5 feet from the wall? So how? When the base of the ladder is 5 feet from the wall. Too much writing, which you probably can't read anyway. Okay, so here's the situation. We've got a 13-foot ladder. I'm going to label these lengths. Anything that changes will get labeled with a variable. So this length here is going to change. I'm going to give it an x. The height you are off the ground is going to change. I'm going to give it a variable y. The length of the ladder doesn't change, so it's going to get whatever its length is. Now, I am told that the dog is pulling the base of the ladder away at 1 foot per second. So x is getting bigger. dx dt is, since it's getting bigger, it's a positive 1 foot per second. They want to know how fast you are falling, or I do. So I want to know what dy dt is equal to when the base of the ladder is 5 feet from the wall. So that is when x is equal to 5 feet. So we've got x's and y's, we've got the rates for x's and y's. We want to find an equation that relates x's and y's. Well, we have a nice Pythagorean right triangle here, so that I know that x squared plus y squared equals 13 squared. If I take the derivative of this with respect to time, I'll get 2x times dx dt plus 2y dy dt equals 0, because the derivative constant is 0. So let's see, I know what x is, that's 5. I know what dx dt is, that's 1. dy dt is what I'm looking for, and I don't know what y is. I need to know what that is to figure this out. So I'm going to go back to the original equation. I know that at the point I care about, x is equal to 5. So that means I've got 5 squared plus y squared is equal to 13 squared. When you solve for y, it's Pythagorean triple, I already knew this, you get y is equal to 12. So now I've got 3 of the 4 variables. I plug in and I can solve for the 4th. So I have 2 times my x, which is 5. dx dt is 1. That's nice. My y is 12, and dy dt is what I'm looking for. Solving for dy dt, make sure I don't get too far down. I have, let's see, 24 dy dt is equal to, bring that over, negative 10. So dy dt is negative 10/24, also known as negative 5/12 feet per second is how fast you are falling. Notice it's negative because you are falling. So the key with doing related rates, and we'll do a lot of examples in class, but the key to doing related rates is figuring out what you know, what you were told. You should always draw a picture, write down what you know, find an equation that relates the things that you know, then take the derivative, fill in what you know, solve for what you need. The hardest part is typically getting this equation, but we'll have lots of examples and you'll have lots of practice, and that's how you do related rates.